Okay. All right. Well, I hope happy Friday, everybody. I hope you guys are doing well. It sounds like you guys are working hard, searching for good data sets, and I look forward to hearing all of your what you found in your proposal meetings and whatnot. So thanks to everybody who's signed up. A couple groups still have not signed up. They're haven't determined their, I guess, proposal time slots. So just want to really push you to do that. They are next week. So and if you're going to meet me on Tuesday, then you need to have your stuff submitted by Monday. And I guess the last deadline to change when your proposal meeting will be Sunday of this weekend. Anyway, I hope as you are searching for data sets, you're asking good questions and asking, is this data set trustworthy and reliable? And that's going to be something that will be valuable, I think, through the rest of your data science career, is always always having a tiny bit of skepticism about data and always asking, can I trust and rely upon this data? Because that's going to be the foundation for any kind of data science conclusions you're going to be making. And so you want to make sure that your data is reliable and trustworthy in the first place. Okay, we are going to take a little bit of a tonal shift in this class. So, a lot of the stuff in the beginning has been about just kind of exploring your data, finding summaries, doing visualizations, and things of that nature. And that, I think, is going to serve you well. And certainly you will need to do that in your project. But I want to take a little bit of a shift here and start moving into more of the, I guess, the statistics part, okay? So beyond just kind of finding, calculating summaries, calculating the mean and standard deviation, things like that in your data, we want to start asking statistical questions. And so that's what we are going to take a look at today. And today we're going to start with just this idea of, like, what if we wanted to compare groups and we wanted to compare the means of two groups, okay? So we've got statistical foundations for comparing groups. And so I've made up this imaginary scenario where we've done a battery experiment. So it says, let's say you find some data containing results from a battery experiment, and the experiment compares store brand batteries from different stores. So, for example, like if you go to, is this going to work? Say Walmart, you can buy their store brand batteries, okay, and it looks their in-house brand is Great Value, and then the other, Target has their in-house brand Up and Up, okay, and you can get these batteries and stuff, and you go to Costco and you have Kirkland and things like that. We'll just pretend we've picked two brands. We'll call them brand A and brand B. And, a friend says, you know what? A lot of these store brand batteries, they're all the same. Okay. They're all produced by some mystery manufacturer, and all they do is they just change the labels on these things. And you're like, oh, well, maybe that's the case. And we're kind of curious about this, and we want to just kind of see if we can test this and things like that. I mean, obviously, I guess you could do an investigative side where you'd like try to investigate the origins and sources of these things, and maybe they'll tell you who their manufacturer is, but maybe that's a secret and they're not going to reveal it. So maybe you just decide, we're going to run an experiment and we're going to test this out. And so we're going to pretend we've got data from the results of an experiment. And the experimenters, what they've done is they built this little contraption designed to drain the battery at a constant rate. So maybe they plug the battery in and it lights up a light, or maybe a motor, a little small heating element or something like that. and it runs down the battery, and they time how long does it take for the battery to start. It starts off at 1.5 volts, and as it runs out, the voltage goes down, and it might be surprising, but a lot of times the battery is considered no good if its voltage drops down to 1.35 or something like that. Okay, and we'll say the data is stored in our CSV file, batteries.csv, and I've uploaded it to Brew and Learn. Okay. Okay, so let's just take a look at our data here, and so we'll load up the tidyverse, and we'll load up our batteries data file. Okay. And our batteries data file just has 2 columns. We've got a column for brand A, a column for brand B, and this is what it looks like. So, all we have are just 12 observations for brand A, 12 observations for brand B. Oh no. Okay. I hope it works. All right. And we have these different runtimes. So, a battery lasted 135 minutes, and this one lasted 138 minutes, and this one lasted only 114 minutes, and so on and so forth. And this is what we have for brand B. What's going on here? Sorry. Okay. And so, our data is in 2 columns here, and if we're going to do stuff in the tidyverse, we need all of our measurements to be in 1 column. I don't know what's going on with our projector, these things. It's very, very touchy. Okay, sorry for the typo. It's supposed to say inspect the data. Okay, so anyway, this is what we have here. And so what we're going to need to do is we're going to have to pivot the data. Okay, so we're going to pivot our data so all of the run times are in 1 column, and then another column will be, does this runtime belong to battery brand A or brand B? So I'm going to pivot them longer, okay? And I will pivot columns brand A and brand B into 1 column, and that will go into the column brand, and then the runtime, the values will stay in the column runtime, and so now this is what it looks like, and everything is in 1 column, and we have a total of 24 rows. Okay, and now I can, this got cut off, but now I can do a couple, I can create a visualization. So one is the box plot, okay, and I apologize for this, and I haven't formally introduced the box plot, but the box plot, you get a, all right, I'm gonna have to load this up. But the box plot will show you basically where the median is. The median is the line inside the box, and it also shows you the top and the bottom of the box corresponds to the 75th percentile is the top of the box, and the bottom of the box is the 25th percentile. So let me go ahead and import the data set. And we're going to go to bring in our batteries data set, okay? And we'll import that, brand A and brand B, great. Okay, so we're happy with that, and then what we're going to do is we're going to pivot this. I pivoted it back into batteries. So I'm going to go batteries, and then take batteries, and we will pivot. Oh, I got it. So library tidyverse. Okay, oops, and then now we'll take batteries and pivot longer. Oh, store this back into batteries. Pivot longer, and we want to do columns brand A and brand B, and we'll go names 2 will be brand, and then values 2 will be runtime. Okay, so this is our data after pivoting. Okay, and then perhaps I think I'll want to arrange by brand. Okay, so this is how we have it, brand A and brand B all here. Okay, and then so now let me plot this. And so what we will have is we'll have y will be runtime, and then x will be brand, and then we'll do geom underscore box plot. Okay, and so this is, here is our plot here. And so if I ask for like if I say batteries and I filter brand equals brand A, and I say select runtime, and then we'll pull it, and then I'll ask for summary. Oh, equals. All right. So here we, this is the summary on brand A, and then I'll do the same thing for brand B. Okay. And so you can see things like the minimum for brand A is 113. The first quartile is right here at 115. The median is at 121. The third quartile, it doesn't plot the mean in the box plot. Third quartile is at 129.8, so right here around just under 130. And then the maximum value is at 138. So this is the box plot. It just basically calculates these values and puts them on the box plot. And then on the right hand side we have it for brand B. The minimum is 117. The first quartile is at 125. The median is at 131. And the third quartile is at 132. And the maximum value is at 142. So these are our two box plots based on basically the 12 observations that we have here. Okay. And that's how we have our values here. Okay, so that is this is the corresponding box plot. Sorry, I got cut off here. We can also just say like, hey, you know what? I want to calculate some summary statistics, right? So I could calculate things like, what is the mean? The mean of brand A is 123, and the mean for brand B is 129. So if I take the 12 batteries for brand A and I calculate the mean, it's 123. Take the 12 batteries for brand B, calculate the mean, it's 129. And so we have a question, does this reflect an actual difference, right? So what does this mean, right? So in our specific sample of data, we got 12 observations from brand A and 12 observations from brand B. The mean runtime for brand A is 123. For brand B, the mean runtime is 129. And so we have a difference of 6 minutes between brand A's average and brand B's average. And this is a difference in our sample. I just have 12 batteries here and 12 batteries here. And so the question is, can I generalize this to like all the batteries of brand A and all the batteries of brand B? And does that mean in general brand B batteries run longer than brand A batteries? Okay, so we want to see if we can kind of generalize what we see in our sample of 12 data points for brand A and 12 data points for brand B. Can we then generalize to all batteries, which we call the population? The population is everything in brand A and everything in brand B. Okay, so we see a 6 minute difference in our sample. Does that mean that in general brand A has a mean runtime that is different or basically shorter from brand B's mean runtime, and thus indicating they're produced maybe at different factories? Or is this result of a 6-minute difference just a random fluke? Okay, maybe it's possible that our friend's claim is true. Brand A and brand B are really have the same in the population, and the 6-minute difference we observed is just due to kind of our random selection process. Okay, maybe we accidentally selected some like poor performing batteries for brand A, and we just happen to select a few better performing batteries for brand B. That's a possibility too, right? So we need to weigh this. Like, we got a 6-minute difference. Does that mean there's actually a difference in the population, or could it just be the result of the random selection process? I don't know. Okay, what do you think? What's your gut feeling here? One group is 123, one group is 129. Do you think that's actually a difference or random selection? Okay, so these are the kinds of questions, and so the answer really depends on like the internal variance. Okay, like, is brand B, like if everything in brand A is like 122, 123, 124, 122, 124, 123, and there's like just a very narrow range, and everything in brand B is also in this very narrow range, we have little variance, then we could say, yeah, there's definitely a difference. Okay. On the other hand, if it's like wildly all over the place, right? Like we have a battery lasts 80 and a battery lasts 200 and a battery lasts 100 and a battery lasts 140 and it averages out to 123 for brand A, and the other one it's like similar. You have these wild numbers all over the place. You have huge kind of internal variance. So we'd say, yeah, you know what, this difference between 123 and 129, probably not that big of a deal. Okay. So yeah, this is kind of what I would say is at the heart of statistical questions and statistical inference is this effort to distinguish actional phenomena from random variation. Okay, so this is what I wrote. A major reason for running statistical tests is to distinguish between actual phenomena and random flukes. And so here's just a few examples. If you flip a fair coin 20 times, what you would expect is you'd expect getting something around 10 heads out of 20 flips. What if you flip a coin 20 times and it lands heads only 5 times out of 20? Okay? Does that mean there's something wrong with your coin or something wrong with your coin flipping technique? Okay? Or could this seemingly unusual result just be random chance with a fair coin? Okay? Maybe in a more consequential case, a clinical trial finds that a new drug leads to improvement in 65 patients, while placebo leads to an improvement in 55% of patients. So you have this 10 percentage point difference. Is this 10 percentage point difference a real effect of the drug? Or, on the other hand, is it plausible that the drug doesn't really do anything and just kind of by random chance we happen to get some patients or participants who did better in this group and some and not as many in the other group, right? That's another question. Perhaps not very consequential, but something that you might encounter in real life is in your day-to-day life is, I don't know if you've ever played board games with friends, okay? And I don't know, sometimes your games involve like rolling dice, like if you play Settlers of Catan or something like that, right? You roll dice, and when you're playing, it feels like, oh man, like the dice I want it to roll the number 5, and it feels like it's never running the number 5, right? And rolling the number 5. And so you might say like, man, I think something's wrong with your dice, okay? And that's a statistical question, because you're basically arguing that the results we're seeing isn't a random fluke, but rather reflects an actual phenomenon that something is wrong with the dice, okay? And maybe there is something wrong with the dice, and that's why we're not getting the numbers we're expecting, okay? Or maybe it's just randomness, and just by random chance and coincidence, we're not getting the numbers we want, okay? And these are the kinds of questions we have, right? Is this something actually going on? Is this an actual phenomenon going on, or is this just random variance? And so hypothesis testing is the framework we use to kind of address these kind of questions. Okay, I have forgotten, I always forget these view quizzes. So let me give you your first view quiz answer. What is it, week 5 Friday? Oh yeah, we're like halfway through the quarter and we only have a few weeks left in the school year. Okay, first answer is D as in dog. D as in dog. Okay. So in our case, what we want to do is we want to compare the means of two independent groups. And so the statistical test that corresponds to that is the two-sample t-test. There are all kinds of different statistical tests out there. Some are for comparing means. Some are for comparing proportions. Some are for comparing, I don't know, multiple, like means from multiple groups, not just two and things like that. But if you have two groups and you want to compare the means, two-sample t-test is what we can do. Okay, and so the way we do a hypothesis test is we take our question and we have to state it as a testable hypothesis. And that testable hypothesis we call the null hypothesis, okay? And what we do, and we call this hypothesis testing, is because we test this null hypothesis that we've created against the data that we've observed, okay? And for a hypothesis to be testable, it has to be a specific claim about the population. And when you make a specific claim, you can then imagine the hypothetical world under that hypothesis. So these words are all related, right? So you have a hypothesis and you say, if this hypothesis were true, what would my world look like, right? So you're imagining this hypothetical situation based on your hypothesis. And for you to imagine that hypothetical situation, it has to be specific. Your hypothesis has to be specific. So our specific specific hypothesis will be population 1 and population 2 have the same mean. Population 1 has a mean mu1. That's the symbol we use for the mean of population 1. Population 2 has a mean. Its symbol is mu2. And our null hypothesis is that these two means are equal to each other, that they're the same value, the same number, whatever it is. So for our example, we've got brand A, and we will say the mean of brand A is mu A, and the mean for brand B is mu B. These are the means of the entire population, okay? That's different from the numbers 123 and 129. 123 is from my sample of 12 batteries. 129 is from my sample of 12 batteries of brand B. And we're trying to say, okay, well, I saw a sample of 12. What does this say about everybody, right? It's kind of like, I don't know, you encounter 12 people from UCLA. What does this say about all the students at UCLA, right? You encounter 12 people from, another university. What does this say about everybody, 12 people from Stanford? And you say, what does this say about everybody from Stanford, right? It's kind of, it's a little bit dangerous to do such a thing, but that's what we have to do in statistics. We don't have the resources to measure every single battery out there. So you have to deal with a sample. Hopefully you have more than 12 observations, but the premise still kind of holds true, even if you only have a small sample. Okay, and so again, when we're testing the hypothesis, we make an assertion, and we say, let's assume the claim made by the null hypothesis were true. Okay, let's assume this statement that mean of brand A and mean of brand B are the same. Okay. And if that statement is true, if brand A and brand B truly do have the same mean, what does our hypothetical world look like? Okay, well, what we would expect is that when we run our experiment with random samples of 12 batteries, what we would expect is that we would expect the run times for the two groups to be equal to each other, or at least kind of close. Maybe we don't expect them to be exactly the same, but we would expect the two numbers to be close to each other. And the question now comes down to, when I look at my data, I have a mean of 123 and a mean of 129. I'm getting a difference of 6 minutes. Is that close to zero, or is that different from zero? Okay, that's the question that we're after. Is a difference of 6 minutes, is that small enough where I can just kind of ignore it? Or is that big enough where I can say, yeah, that's actually different, okay? So if the null hypothesis were true, I would expect the difference to be zero or close to zero. And the question is 6 minutes close to zero, okay? So, just kind of thinking out loud, we say, I know individual batteries have different performances, and my 12 batteries were selected randomly. And so the means that I have, 123 and 129, are affected by the random selection, right? It's possible that just by random chance I happen to get some high-performing batteries. And it's also possible that by random selection I happen to get some lower-performing batteries, right? It's like whenever you randomly select things, sometimes by good or bad luck, you get things that are different, right? If brand A and brand B do have the same mean, what's the probability? We can ask, what's the probability that this random process of selecting 12 batteries could produce a difference of 6 minutes, just kind of by random chance? So that's kind of the question. I actually have a difference of 6 minutes, so we're asking, could a random process also just produce this difference of 6 minutes? Okay, that's what we want to know. And so we have to do some calculations. And so the answer to that question, when we calculate the probability, is known as a p-value. We're asking, what is the probability that randomness could produce a difference of 6 minutes? Because that's what we got in our data. 6 minutes or more if the null hypothesis were true, if they're actually the same. Okay, so the p-value is the probability of observing the statistic in our data or something more unusual if we assume the null hypothesis were true. And we're asking, okay, what's the probability of getting a difference of 6 minutes if population 1, brand A and brand B, actually have means that are equal to each other? And so I want to talk about, before we actually do any calculations, I want to talk about the implications of getting a big p-value or a small p-value, okay? And so one possibility is the outcome is we do our calculations and our p-value is small, okay? Our probability is small. What does that mean, okay? It says that means the probability of getting a difference of 6 minutes is unlikely to be observed, okay? And so then the fact that you actually did observe a difference of 6 minutes, which is supposed to be unlikely if the null hypothesis were true, gives us reason or evidence to believe that the claim made by the null hypothesis is wrong, okay? Because again, the scenario here is if brand A and brand B actually have the same mean and we do our calculations, it says, yeah, the probability of getting a 6 minute difference, that is really small, okay? But we actually got a difference of 6 minutes. And so the fact that we actually got a difference of 6 minutes tells me this original claim probably wrong, okay? It's kind of like, if you have a fair coin, what's the probability you would flip heads 20 times in a row, okay? It's really, really small. It's like 1 in a million, okay? 1 in a million. If you have a fair coin, the probability of flipping heads 20 times in a row is like 1 in a million, okay? Let's say somebody takes a coin and they flip it 20 times in a row and they get 20 heads, okay? You would say that shouldn't happen with a fair coin. It happens 1 in a million. And so the fact that it did happen says, you know what? I don't think that's a fair coin, okay? And that's basically what we're saying. We do our calculations. Our calculation says this kind of thing shouldn't happen very often. It happens maybe like 1% of the time. And so the fact that it did happen tells me, I think my initial assumption that these two things are the same is wrong. So if you end up with a small p-value, you're going to reject the claim made by the null hypothesis. We conclude that the reason why we're seeing a difference of 6 minutes is because brand A and brand B don't actually have the same mean, okay? On the other hand, let's say you do your calculations and the p-value ends up being large, okay? It says this getting a difference of 6 minutes, not unusual. It's not unusual, right? The null hypothesis says that our two means in our populations are equal. And sure, we would expect our samples to have means that are equal or a difference that's close to 0. Okay, the sample mean of x bar A and x bar B, that difference we also expect to be 0. Maybe we get a difference of 6 minutes, but it turns out our calculations say, yeah, you know what, a difference of 6 minutes, not that unusual. Okay, and so that would say we have no reason to believe that mu A is different from mu B. Okay, now that is different from saying mu A is equal to mu B. We're saying we don't have a reason to believe that they're different. Okay, so we don't have enough evidence against this claim, and we do not reject the claim made by the null hypothesis. Okay, again, it's kind of like if you have a coin and we're going to flip it 20 times, what do we expect? I expect to get 10 heads out of 20 flips. What if I flip a coin 20 times, and I get 12 heads out of 20 flips? Okay. Do we suddenly believe that my coin is unfair? Probably not, because it feels like a fair coin could reasonably land heads 12 times out of 20 without any kind of trickery involved. Just by random coincidence, we could get 12 heads out of 20 flips. That doesn't feel unusual. If we calculate the probability, maybe that's going to happen like 20% of the time. I don't know, I'm making up numbers, but something like that could happen 20% of the time. It doesn't feel that weird to get 12 heads out of 20 flips. And so if I get 12 heads out of 20 flips, I'm not going to suddenly conclude that my coin is unfair. Okay? Does it mean my coin is fair? I don't want to jump to that conclusion either. Perhaps my coin is actually a little bit unfair, and that's why I'm getting 12 heads out of 20 flips. But right now, it doesn't look that different from a fair coin. You have a question?
Yeah, sorry, I'm still a little bit confused. In the paragraph, it says a difference of 6 minutes, which is more than 0. Our calculations show that this kind of difference is not considered to be unusual.
Yeah.
So it is considered to be usual to have 6 minutes of difference.
This is a potential outcome. So I haven't done any calculations yet. I'm just saying, let's imagine we do our calculations. In one scenario, we get a tiny p-value. What does that mean? Okay. In the other scenario, we get a big p-value. Okay. So if you were to get a big p-value, it means whatever you've observed in your data is not unusual. Getting a difference of 6 minutes is not unusual. Getting 12 heads out of 20 flips is not unusual.
If it is not unusual, which is kind of like usual, which is like the normal case.
Yeah.
But it's like contradicting because it says it should be like mu A should be the same as mu B.
Yeah. So again, again, when you flip a coin 20 times, what do you expect? You expect 10 heads, right? What if you get 12 heads? Okay, it's a little bit different from what you expected, but is it enough for you to say my coin is unfair? It's not. Not really, right? It's different from what you expected, but it's not that different. It's not that unusual, okay? On the other hand, if you flip 20 times and you get 20 heads, okay, that's very different from what you expected. You expect 10 heads. Getting 20 heads out of 20 flips feels like that shouldn't happen, okay? Is it theoretically possible? It is, and I think it happens with a probability of 1 in a million, okay? It is theoretically possible, but it seems so improbable that we're going to just say, yeah, it shouldn't happen like that. It shouldn't happen like that, okay? But getting 12 heads out of 20 flips, it's not exactly what we expected. We're expecting 10 heads out of 20 flips, but getting 12 heads out of 20 flips, not that weird, okay? And that's reflected with a large p-value. If you do the calculations, you say, what's the probability of a fair coin landing heads 12 times? And I don't know, it's some number.
In the flipping coin example, what will be the null hypothesis?
The null hypothesis would be that you have a fair coin that lands heads 50% of the time.
Small, which is shown by the large p-value.
Yes.
So even if it is not completely the same as what we expected, but it's not big enough so that we have to.
Right. So the question is what I'm observing a 6-minute difference, a big difference from what I expected? What I expected is a 0-minute difference. If the null hypothesis were true, I would expect a 0-minute difference. And the question is a 6-minute difference big, or is it not that big? Okay.
Not that big, so we don't.
So this one is, if you end up with a p-value that's large, that means 6-minute difference isn't that big. If you end up over here, if you end up with a p-value that's small, that means a 6-minute difference is big. Okay, and it really depends on kind of like how much variation you have within the thing, right? And it's going to be different for every scenario, right? So, a 6-minute difference, I don't know, is that a big deal or not? For holding your breath, like that's a big difference, okay? But like waiting in line or waiting in traffic, from going one end of the city to the other, maybe not that big of a difference, right? So it depends, okay? All right, whether we say our p-value is large or not, so our p-value is going to be a number. It's a probability. It's going to be between 0 and 1. We have to draw some kind of threshold. That's determined by our significance level, alpha. And so if our p-value ends up less than alpha, it means our p-value is considered to be small, and we would reject the null hypothesis. If the p-value is greater than alpha, then our p-value is considered to be large, and we do not reject the null hypothesis. Okay, so we just have this arbitrary number, and this is the threshold. If our p-value is smaller than that, we reject it. If it's larger than that, we don't reject it. The most common choice for alpha is 5%. We say if it happens less than 5% of the time, that's rare enough for me to reject the null hypothesis. And if it happens over 5% of the time, we're not going to reject the null hypothesis. You might be in a more strict scenario and you say, I want to just pick 1% or 2% or something, a number smaller than 5%. Usually we don't go much bigger than 5%. Technically you could use like alpha equal to 10%, but usually we don't go over 5%. Okay, we're gonna run out of time. Let me give you your second view quiz answer. Second view quiz answer today is the letter C. C as in cat. C as in cat. Okay. All right. So we're gonna take a look at a couple more key statistics. So we have the mean, the average runtime for brand A and the average runtime for brand B, 123 versus 129. A lot depends on kind of the internal variation, and so that's measured by our standard deviation. Okay, so our standard deviation says, are the numbers all very similar to each other? Okay, like if you have small standard deviation, it means all the numbers are very close to each other. If you have a big standard deviation, it means our numbers are a lot different from each other. Okay, we have a standard deviation of 9.3 and a standard deviation of 7.25, so medium amount of standard deviation. Okay, our hypotheses is that the two means are equal to each other, and our null, that's our null hypothesis. And the alternative, okay, so we're testing the null, and if the null isn't true, then the alternative is going to be that the means are different. Sometimes you can have an alternative that has a greater than sign or an alternative that has a less than sign. Those are called one-sided hypothesis tests. So I'll probably have to come back to that later, okay? But for now, we're just going to say, hey, are they equal or are they different? And so our alternative hypothesis says that the two brands have different runtimes, okay? And it would be interesting to us if brand A lasts longer or brand B lasts longer. Either of those would be interesting. Okay, so our question is, what is the probability of getting a difference of 6 minutes from random chance? The answer to that is our p-value. Okay, this is the probability that we have to calculate. So I'm going to extract these values. I've got the brand A values. I filtered to brand being A, select the runtime, pulled them out. These are my 12 values, and these are my 12 values for brand B. Okay, and are these different from each other? So within R, there is a function called t.test, and this just performs the t-test, and this compares. the two means, okay? And we get the conclusion, or the result, is a p-value of 0.09335, okay? So again, brand A has a mean of 123, and brand B has a mean of 129, and we do our calculations, okay? And these are like a little bit more technical stuff. We don't have to get into this stuff, but our resulting p-value is 0.09. So it just means, you know, if you have data that look like this with this kind of amount of variation, just imagine a big population. If you had a population where all of the numbers have the same mean, right? It's just one actual population, and I just happened to select 12 values and another 12 values, and I calculate the mean of these 12 and the mean of these 12, is it possible that I get a difference of 6 points or 6 minutes? Yeah, it could happen. How often does something like that happen? Not very frequently, but also not that infrequently. It happens around 9% of the time, okay? So our threshold, if our threshold is 5%, is 9% over than that, right? That would fall on the large side, okay? So this top line here in the results of the Welch two-sample t-test, this is what we call the two-sample t-test, our p-value is 0.09335, okay? So the interpretation of that is, if there's one factory that just produces brand A and brand B, is it possible that by random luck we end up with 12 batteries from brand A with a mean of 123 and another one by another sample where the mean is 129? It is possible. How often does that happen? It happens with a probability of around 9.3%. And the question now is that a big enough number? And again, it's not huge, but it's also not so small that we can just ignore it. So our threshold, we use 5%, 9% is bigger than that, so that falls on the large side. And so our decision is to not reject the null hypothesis. Our p-value is quote unquote larger than our threshold. And so that means our observed data of a 6-minute difference could be produced by randomness even while the null hypothesis were true. And even if our observed data doesn't match the null hypothesis exactly, it's not that unusual. And so based on the data we've collected so far, we are not able to make a definitive conclusion, and it's possible that brand A and brand B have the same mean, and our results are just the results of random chance, okay? But does this prove that brand A and brand B do have the same mean? No, okay? So all we're saying is I don't have enough data, right? 12 batteries from brand A and 12 batteries from brand B isn't enough for me to conclude that they are different, okay? So it is possible that they actually are different. It's just right now I don't have enough data to really feel confident about saying that they're different. So right now I'm going to say I don't have enough evidence to say anything really, okay? I don't want to say that they're different, okay? I'm also not allowed to say that they're the same. I just have to say I don't have enough evidence to say that they're different, okay? So one thing you have to be careful is you don't ever want to use this phrase, we accept the null hypothesis, okay? All you can say is I have enough evidence to reject the null hypothesis. Like if you get a 20-minute difference, that's probably going to be enough for you to say, yeah, I've got evidence that brand A is different from brand B because I've got a 20-minute difference. Okay, I reject the null hypothesis, okay? But here with a 6-minute difference, it's not big enough. And I would say I do not reject the null hypothesis, okay? But we don't want to say I accept the null hypothesis, okay? Just because we didn't reject the null hypothesis doesn't mean the null hypothesis is true, okay? We're not saying that brand A and brand B do have the same mean, okay? All we can say is that with only 12 batteries from each brand, a difference of 6 minutes is not enough for us to make a definitive conclusion. Okay, all right, so here is, let's say we have a larger data set. I've collected more data and I've just made up some more numbers. Now I have 36 batteries for brand A, 36 batteries for brand B, and let's say the mean is still 123 for A and 129 for brand B. Okay, now that I have more data collected, maybe this 6-minute difference is now going to be significant. Okay, so if you have more data, then it kind of backs up. Like now you feel a lot more you feel more strongly that the mean of brand A is really around 123, and you feel more strongly that the mean of brand B is around 129. And so if I have 36 batteries, again, all I do is I do t.test and I just put in the vector of all of the numbers and R does the rest. So t.test A and B, and now I get a p-value of 1%, okay, 0.01. So if my threshold is 5%, this is smaller than that, okay? So the question is it possible that just by random coincidence, I happened to get 36 batteries where the average was 123, and I happened to get 36 batteries where the average was 129, even though they're all coming from the same population? It's possible. Does something like that happen frequently? No. Okay? Again, it's kind of like if you flip a coin 20 times, can you get 20 heads in a row? It's not impossible, but does it happen frequently? No, it happens like 1 in a million. Does it happen frequently where you would get 36 batteries with a mean of 123 and 36 batteries where the mean is 129? It's possible. Does it happen frequently? No. It happens by random chance around 1% of the time. Okay? And we're going to say 1% is small enough for me to say, I don't think it happened by random chance. Okay? And so compared to our threshold of 5%, this would be considered a small value, right? And just for like kind of a gut reaction, like if I had a deck of cards and I said, and I pick out a card at random and I say, go ahead, name a card, and you name 5 of clubs, and I flip it over and I show you it's the 5 of clubs, like you'd go like, whoa, right? Like your gut reaction would be surprised, right? Technically, that has a probability of around 2% because it's like 1 in 52, okay? 1 in 50. So I have a 2% chance of that happening. And your visceral reaction is like, oh, that's impressive. Like you got the card I selected, okay? And so here, if we get a p-value of 1%, that's like, I guess doing the same trick, but with like 2 decks of cards, okay? It's like even more impressive because it's now even more unlikely, right? So that's kind of what it is, right? So compared to our threshold of 5%, this is a small value, and so we would say we would reject the null hypothesis. Okay, I guess I'll just make you read these slides on your own. How many answers did I give you? 2. Okay, third answer then is the letter E. E as in elephant. E as in elephant. Okay, so we'll wrap things up here. Have a good weekend. I hope your search for data is going well. I think most of the groups have scheduled their meeting time. I think everybody's requested Thursday, but and that's fine. So I look forward to meeting with you guys on Thursday. Make sure you submit your questionnaire. If you're scheduled for Thursday, make sure you submit it by Wednesday. If you're going to schedule for Tuesday, make sure you submit it by Monday. All right.
The questionnaire is just the R&D proposal.
Yeah. Just fill out that questionnaire and then put in the links. Okay. Make sure you put the links in for your data there. Yeah.